Okay, so today, let me get this here. There we go. Today, we are going to look at and start chapter 4. And chapter 4, we're looking at linear relationships. And correlation. So that's what we're going to talk about today, and that's our chapter 4. We'll be in chapter 4 for this entire week. So first we're going to talk about what we're doing here in chapter 4 and what we're working with, and that is bivariate data. And all bivariate data means is that we're looking at two variables. So I want you to know we're still in this numerical data. Remember a few weeks ago, I mentioned that we're going to kind of leave categorical data behind us for a few weeks and just focus on numerical data. And we did that last week with chapter 3. And we're going to continue that here with chapter 4. So numerical data and bivariate means that we're studying two variables. And those two variables are going to be X and Y. X is what we call the explanatory, whoops, forgot my E, explanatory variable, and Y is what we call the response variable. So an example of this is we're looking at maybe height and weight of individuals. So I have height, which is going to be my X, my explanatory, or maybe my predictor variable, we might call it, and weight, which is Y, which is my response variable. So keep in mind what this means is that the explanatory, my X variable, will explain or predicts the response. So when we're looking at this, my Y here, you need to be able to look at data, and if we have two variables, know which one is X and which one is Y. So which one is the explanatory or the predictor and which one is the response. Now, you can look to see, sometimes it's very obvious. Height versus weight, I want to know if the height can explain someone's weight, that kind of thing. So can someone's height predict someone's weight? Okay, that's the kind of thing I'm looking at here. And when we have this bivariate data, we have a graph, of course, that we can study. And so we're going to do that first. And that is called the scatter plot. And all the scatter plot is, it's just a plot of each X, Y pair on some axes, and that each XY pair is a dot on the plot. So let's take a look at an example of what this looks like. So when I have a scatter plot, I'll do it of this example here, the height and the weight. And what we're looking at, some X, Y here. And I have height down here. That's my explanatory variable or my predictor. It predicts the weight, which is the response variable over here. And what we're looking at, it's just dots. And here, and we might have one over here, and one over here. Okay. So what we're looking at here, these are each XY pair. So what I did was I took a study and I just sampled a few people at RIT, and I just stopped them and I said, okay, what is your height? What is your weight? And that is an XY pair, right? So an XY pair is that one individual's height and that particular individual, their weight, okay? So that is a pair, so that is a dot. So each dot on my plot represents one individual, okay? And that is a scatter plot. When we look at these scatter plots, we can describe the relationship that we see between X and Y just by viewing this plot. So when we do that, let me write this down. So I want to describe the relationship in the scatter plot between X and Y. So I don't have anything numerical to back up anything I'm saying. I'm just going to view this scatter plot and give some information based on what I see here. So the first thing is I want to know the trend of what's going on. So as my X increases, so as X increases to the right, what is happening with my Y, my response? My Y is also, in this case, increasing. So here I would just say, as X increases, my Y, and then I would fill in the blank. So I would say, okay, well, it's either increasing or decreasing. Okay. So when we're looking at this and we're telling if X is increasing, what happens with Y? I don't want you to explain to me as X and Y. I would like you to actually say as height increases, then the weight is also increasing. Do you see that? So as height is increasing, weight is increasing as well. That's what I would like you to say, because I don't know what X and Y mean if I don't have this information here. So you have to tell me what X and Y actually stand for. So I don't like to see an X and Y. The next thing we want to do is we want to know if we see a pattern in the graph. So do we see a pattern? Now the pattern could be linear or it could be curved. It could be a specific curve. It could be quadratic, right? So if we see a pattern, we want to make sure we say that we see a pattern. So yes, we might say, okay, as X is increasing, Y is also increasing, and it does look like we have some sort of a linear relationship. So it's showing a linear pattern. And then lastly, of course, we always want to include those outliers. We want to know, do we see any outliers? So as we started mentioning last class, we keep bringing up these outliers, these unusual values, and what does that mean to us? Well, remember last week we started talking about quartiles, and when we looked at quartiles, we noticed that they're resistant to outliers. So they're a good measure to use if we have outliers because they're resistant. So the outliers don't affect those values. So that's important for us. So that's why we're always looking to see if there's unusual values or outliers in our data set, because they may have an effect on some values that we get numerically, and that makes a difference if we're going to use that value and actually trust that value for our data. Okay, so that's why we're always checking in on that. We're always looking to see if we have that. So this is what we're going to do when we're describing the relationship that we see in a scatter plot. Okay, so we talk about these three things. So in this example here, I would say, like we already mentioned, as height is increasing, weight is also increasing. I do see a pattern. It does look fairly linear. So the way I know that is if I lay the pen right there, it almost covers all the dots right in the middle, right? So it's linear. They all follow that straight line. But I do have something a little odd here, right? I have this value here and I have this other one over here. So what happens is these look like outliers, right? They look different from the rest of this data. So they look unusual. So I would mention that it appears that I have 2 outliers for this data set. And that's all we're looking at. You're just truly looking at this and just making some observations about the data, the paired sets, okay, based on just what we see. The next thing we're going to talk about is that there is a numerical measure that we can put with these scatter plots. And just keep in mind, when we first start assignment 6, I just want you to look at it and do what we just talked about. And then later on in assignment 6, we're going to do this part and actually calculate some values. And the value here is called the linear correlation value. Now, in your book, it may be called the linear correlation coefficient. The reason why I don't call it a coefficient is because we see coefficient pop up several times throughout the class, and then it starts getting confusing for some of us. So I just call it a value. Keep in mind your book may say linear correlation coefficient. And what this value is it measures the strength of a linear relationship between my 2 variables, x and y. So I need to underline this right here, maybe like a red or green, linear relationship. This is a linear correlation value. It measures the strength of a linear, meaning a straight line relationship. It will not measure the strength of a curved relationship. So if you have a scatter plot that has curved, it may be a relationship between x and y, but it might not be a linear relationship. So this is only for linear relationships. So I have notation to show you, of course. So the first one is for the population, and this is a Greek letter which is called rho, which we will not use often because we're usually looking at a sample. So this is my population correlation. And then we have R, which is our sample correlation. We're going to use R most of the time. Okay, we will see that almost all of the time because we're almost always studying a sample. So I want to show you a few things. So first of all, R is between -1 and +1. So -1 is less than or equal to R, which is less than or equal to +1. So I'm going to write out the scale so you know what these mean. So if R is between -1 and +1, -1 is over here on the left and +1 is on the right. And it leaves 0 right in the middle. Okay. This is going to be the scale for what R represents in the strength. So first of all, if we start at -1 and move up to -0.8, this actually would indicate a strong linear relationship. And so would, on the other hand, if I'm at +0.8, working my way up to +1, any values in that range would indicate a strong relationship. Then from -0.8 to -0.4, I would consider this a moderate strength relationship. And same thing with 0.4 up to 0.8, it would be moderate in strength. Then everything in the middle here, from -0.4 all the way to +0.4, this would be considered a weak linear relationship. And if we have an R value right here of 0, this indicates no linear relationship. So remember, we're looking at the relationship between X and Y. So if I have an R that is 0, it means I have no linear relationship. Again, linear is popping up. That's what R measures, is my linear relationship. So it doesn't mean that X and Y don't have a relationship at all. It just indicates that it's not linear. So you may show a strong relationship that's curved, and you would still have an R value of 0 because that is only for linear. Okay. So I just have some information about R here. Try to show it all a little bit. So if we get an R value that is -1 or a +1, these R values are indicating a perfect linear relationship.
Professor, I have a quick question.
Yes.
Would it always be on the scale of -1 to 1?
Yes. That's what I was writing right here. It's only between -1 to 1. Yep. And if you're at the extremes, then that means it's a perfect linear relationship. So that means that your X and Y would line up in a perfect straight line. R is affected by outliers. So when we're looking at quartiles, we said they are not affected, they're resistant to outliers. That's not the case here for our linear correlation value. So when we see outliers in our data set, it is going to make R not so strong. So what I mean is, maybe my relationship might be a -0.8, and it's going to bring it down, like, it's going to bring it closer to 0 when I have those outliers. So it's going to weaken the R value because that one value is outside of that relationship, like showing that strong relationship. Okay, so it is affected by outliers, and that's good to know, because if we have a whole bunch of outliers, then maybe we shouldn't trust our R value. Maybe it's not a good measure for our data set, that kind of thing. I'm going to give you the calculation for R. We're never going to use this, so you don't have to write it down. I just like to give you guys the calculations so you see them. But, and I'll go over what these all are in here, but I just like to give it to you. It is a little bit of a scary calculation. It looks scary. We're never going to use it. We're never going to do this by hand. We will always use our technology to get this value for us, and you're going to see how to do that on your team assignment today. So Xi and Yi, I think we know by now these are my data values, so I wasn't going to write that down, but X bar we know is our sample mean, and so is Y bar. Y bar is just the sample mean for the Ys. And same thing for Sx and Sy. These are just the sample standard deviations. Just so we have that. And then of course, N is the sample size. So how many individuals we have in our sample. But again, you don't even have to write this down. We're never going to use this, not even in class. I'm not going to do it by hand. It's not worth it. We have our technology to do it for us. I just like to show you what the calculator is actually doing behind the scenes, and that it is more complex than what we would like to do by hand. So again, you'll see those instructions for the calculator and Minitab on your assignment today, assignment 6. Okay, so let's take a look at a couple examples of things that we might see with these scatter plots. So if we have a scatter plot, we have our explanatory down here and our response variable over here, then I might have these dots, and they might form a pretty strong relationship. They might show a pretty good relationship right here, right? We can see it, like you could draw it. You could kind of draw it, right? You could draw the curve and it follows this curve. So in this case, I would say, yes, it looks like it's a fairly strong relationship, but it's not linear. So I would say there's no linear or it's a non-linear relationship. And in this case, my R value would be close to 0 because R is only measuring my linear relationship. And there's no linear relationship, so R should be close to 0. If R is 0, it means there's no linear relationship.
Professor, what do you have? What is that on the y-axis? I can't.
Right here, response.
Okay.
RESP. I'm just abbreviating for my response. So it's always my explanatory and my response. Yep. Thanks for asking. Again, I'm going to do the same thing. Response and explanatory variables, or you could call them predictor variables for your X that predicts the Y. Whatever you want to call it, it's just a couple different terms for the same thing again. So here, if we have maybe something like this, okay? Now this definitely looks linear. And what I would do is I would just say, okay, I'm gonna try to see, oh yeah, it follows a straight line pattern. You don't have to do that, I'm just showing you. So this looks like it's a linear relationship, right? And if I'm looking at this and I'm just looking at the graph, I don't have an R value to go with this, I would say this looks fairly strong, right? They're fairly close to one another. So I would say it's strong or moderately strong. And I'm going to take a look. If we were in algebra class and we were looking at this line, we would say, okay, well, the slope of that line is negative, right? So as X increases, my Y is decreasing. It gives me a negative slope. So I have a strong negative linear relationship. And this is where the negatives and the positives come into place here, okay, on my scale. So the negative is actually indicating that direction of the line, so the slope of the line, and it's saying, okay, if it's positive, that means as X is increasing, Y is also increasing, and if it's negative, it's saying as X is increasing, Y is decreasing. So here I would have something like an R value, maybe of like negative 0.87. I'm just throwing it out there, just putting something different than just 0.8. I'm just saying, for instance, I'm just guessing what it would be, right? I didn't calculate anything right here, I'm just guessing. And then I would say, okay, well, I have a strong negative linear relationship between X and Y. Does that make sense? If we went back, and I didn't mean to like zoom that in, I was like holding the paper up. If we go back to this example here, the first one I wrote out with height and weight, and we could see, okay, yes, we have a linear relationship, right? I could draw a straight line or put my pen over it and say, okay, yes, it covers those dots. It looks pretty linear, right? This, I would say, okay, that I have a fairly strong linear relationship. And the reason why I say fairly or moderately strong is I could cover these almost all with the pen. But then look at, I have these outliers. So I would say, well, I have a moderately strong linear, positive linear relationship. Sorry, positive is because X is increasing, Y is also increasing. My slope of my line is positive. Between my height and weight. And I would mention that it appears that I have 2 outliers. So in the beginning of assignment 6, you're just doing this. You're just looking at this and you're going to state and kind of talk about, address these 3 things basically. Then later on in the assignment, like on the, like after you're done doing that, then you're going to start looking at R values. And I want you to actually make a statement about the strength based on our scale here of R. Okay? That makes sense? Pull that last one up here. If anyone needs to see that. Okay, so that's all I had.